Good morning. Good morning, everybody. So I'm here to introduce our speaker today. Muzzamal Iqbal Shaukat will present his work on dark-soliton Qudits, a novel quantum information platform. And Muzzamal keeps his bio sketch simple. He writes in his bio sketch, I did my Ph.D. from higher Technical Institute in Lisbon, Portugal, then joined Institute of Telecommunication, Lisbon, Portugal, as a postdoctoral researcher, then worked as an assistant professor at National University of Sciences and Technology and as a visiting research scientist at the University of Texas at Dallas. Now I joined Texas A&M as postdoctoral researcher. But as I was doing my little research this morning, on Muzzamal, I found that, of course, there are a lot of interesting events missed, and somewhere in between those lines, Muzzamal spent some productive time at the at the Abu Dhabi University at the Department of Electrical and Computer Engineering, and also at the School of Natural Sciences, National University of Science and Technology in Islamabad, Pakistan, where he has done some interesting work on the properties of sudden death of quantum entanglement, and of course a lot of work on solitary structures, solitons, nonlinear Schrödinger equation, the properties of nonlinear wave equation, Schrödinger equation, Landau-Ginzburg equation in different systems, from quantum condensates to electron positron plasma. So there's a rich background, and I think Muzzamal will give us a flavor of his work today.
Thank you so much for a very nice introduction. And so let me start with respect to that. So today I am going to discuss a recently developed novel approach to use dark solitons as building blocks of quantum information theory. And for that, basically, we use the Bose-Einstein condensate with the set of the impurities. And that was already, researchers have done that experiments, proof with respect to the solitons. And we are fortunate enough regarding that. We use that platform or those systems in quantum information theory. So first of all, I would like to discuss very briefly, not in too much details, what is soliton and how is originate and how to obtain the low density dark soliton. Then I will divide my presentation in 3 sections. In section 1, we will discuss how the impurities can be immersed with the Bose-Einstein condensate to separate exactly 2 or 3 level system. And in accordance, we will see by using Wigner-Weisskopf theory, what will be the lifetime or what will be the decay rate of these 2 or 3 level systems. Then in section 2, a fundamental question arises, if we place 2 dark-soliton qubits together, what will be the role of repulsive interaction first? And then we will see if there is a less repulsive interaction or if somehow we can ignore that interaction, then how can we generate entanglement or can observe the decay of entanglement with respect to that. Then in the last section, we will see how these 3 separated levels can be used to see the acoustic analog of electromagnetic induced transparency. At the end, I will summarize my results and will briefly discuss other research projects, as the professor has already told you some of the briefly background of that one. But that I will discuss very briefly. So John Scott Russell in 1834 made a discovery of the wave of translation when he was traveling in a canal, and he observed that this wave has a permanent shape and can travel over larger distances without changing its shape. He also observed that this wave can never merge, 2 waves can never merge like a linear wave. That's the question basically arises of the soliton origin. Then the scientists have a question, many researchers have a question in mind, why and how all this happened. Later on, the research was going on, of course, too much background involved in that, but I'm not including that as well to focus on my own research. However, later on, the researchers determined that this all happening, the travel of this permanent shape is due to the precise balance between the dispersive and nonlinear effects in the system, which the scientists named as a solution of many nonlinear partial differential equations, like the Korteweg-de Vries equation, Sine-Gordon equation, or the Gross-Pitarski equation, which is the main concern equation of my model here. And if we see that there, GB is playing a very important role where the interparticle or the particle interactions can be repulsive or can be attractive. It makes two different types of solitons depending on different conditions here. Fortunately, I would say that we have this particular mathematical model with respect to the Bose-Einstein condensates, quasi one-dimensional, where the interparticle interaction is repulsive here. And the solution is represented with this Bose-Einstein condensate is represented by this equation, with that solution of the soliton is particular of this form, where the important point is N0 is the background number density, of course, but V is important factor here, which is the speed of the soliton. This V can be 0 and V cannot be 0. But let's assume that very simple case where V equal to 0, mean to say that stationary soliton. We have a very simple solution with respect to that size soliton here. But if, however, we are not considering V equal to 0, we can also use that model where V approaches to CS, this dip is going to be decreased, and later on V equal to CS, there will be no soliton existence appear here. Now, the other point, which I was very fortunate regarding that, scientists have already determined that experimentally, the Bose-Einstein condensate, the presence of the dark soliton in Bose-Einstein condensate, if we will see that. Now, this is the background, very brief background in terms of that one. Soliton existence already appear, Bose-Einstein condensate with dark soliton experimentally already perfected in the lab. But what we did to consider this for the quantum information protocols, basically. Now the question comes with that. So we use this Bose-Einstein condensate immersed with the dilute set of the impurities, where these wiggly lines shows the quantum fluctuations, and this shape is the dark soliton, which you have seen on the last slide here. And this model is predicted by this coupled Gross-Pitarski equation, psi1 for the Bose-Einstein condensate, psi2 for the set of the impurities. And here G11 is the interparticle interaction, which we have considered as repulsive for the BEC particles, and G12 and G21 is the interspecies interaction of the impurity and BEC particles. Now we have considered G2 to equal to 0 because the soliton impurities interparticle interaction is 0. So this soliton is not perturbed by the presence of the impurities. And these impurities are much dilute and much massive than the BEC particles. Then this soliton, the impurity particles act like a free particle to consider this, or to the soliton act like a potential for these impurity particles here. And just this is the simple model now comes with that. We have, and after doing some little bit mathematics, you can say that's a simplification, we determine the energy spectrum, where this N depends the number of the bound state, and nu is the parameter which depends on the coupling between interspecies to interparticle interaction and the mass ratio of the BC and impurity particles, where this which plays very important role, which you will see on the next one or two slides. If we go beyond, if we somehow see this expression and somehow do something mathematically, we have done everything, which I am not doing the detail of mathematics. I'm not including on my slides. But if someone is interested, we can do that later. See that if somehow we have the new parameter range in the range of 1/3 to 4/5, we have exactly perfected two separate states. And we analytically determine the states eigenfunctions, which is exactly like, looks like a harmonic oscillator here. The question with respect to that, which we have considered is two-level system considered to be a qubit now. It means to say that. But of course, there are some properties of the qubit, like the degeneracy, spin up goes to spin down goes to spin up. And for that, there is a degeneracy in the state between this range parameter where the qubit is ill-defined due to that degeneracy, which you will see on one or two slides later. Now, the question comes with that, if we go beyond this 4/5, there should be some range for the 3-level system. You can see that by following the similar analysis. Now, anyone can think about that. If we go beyond this 9/7, this means that the 4th level will appear with some range. If we go beyond that range, 5th level appear, and so on. But to do this analysis, first we think that, can we check this process experimentally? Or if someone is interested to do some experiment, so do these 4th, 5th, 6th level appear or not? Okay, so I was telling that if we go beyond this 9/7, 4th level, 5th level appear. But to confirm that we have a 2-level or 3-level system, if someone is interested to do the experiment on that process, we check that numerically. And if we see that these ground state and first excited state results exactly numerically and analytically matches exactly. But there is a little mismatch between the second excited state or the 3rd level which appears here, which tells us that impurity particles are playing very important role. Maybe due to scattering or some other phenomena, the impurity particles are going to disturb the soliton presence here. So it means that in that aspect, we observe that if somehow we are considering the impurity particle very carefully, what type of impurities we should choose in accordance to that mass ratio between these two, then this little mismatch can be avoided. We can avoid that one as well. It means that, but to appear for the 4th level, 5th level, or so on, we need to be very careful regarding what type of impurities we need to use. Okay, and so it means that now we are in that condition for the qubit or the qubit, we can perform some very interesting results with respect to that one. We can consider this model for the fundamental characteristics of the quantum information theory or the other protocols. We can use that one, and for that, to confirm that one, we need to observe what is the lifetime or the decay rate of the qubit or the qubit first. First, we need to understand that one. But before that, let me do that something. Okay, we observe that the transition frequency depends on the interspecies interparticle interaction for the range of this qubit. Of course, we can see with respect to the qubit as well, with shaded region of that one within this range. If you will see that at some new parameter 1/2, there is a degeneracy in the state with the qubit is ill-defined. What I was telling with respect to that, first I will explain you 1 or 2 slides later. So it confirms that like the spin up goes to spin down or spin down goes to spin up, very similar to that one. After that, after observing this phenomena, we need to find out some interesting Hamiltonian with respect to this model. And of course, I will not say that we just pick this Hamiltonian and write everything. No, we need to understand that how we get this Hamiltonian. We use Bogoliubov theory and quantum fluctuation perspective. We define many interesting things here. We use many assumptions like rotating wave approximation and other things to determine this Hamiltonian, where this sigma is going to be the system operator for the 2-level system. If we are considering the qubit, if 3-level system, we have to define very similar way the system operator. BK, which are the quantum fluctuations or the phononic environment, which makes an environment with respect to that qubit system. This is the quantum fluctuation of the phonons, BK represents. And GK is the interaction between the system and the environment. And we obtain this Hamiltonian by using rotating wave approximation. And also, we ignore this at this G interband terms with small value of this coupling coefficient and using this resonance condition here. And similarly, if we want to go for the 3-level system, we can determine by following the similar analysis, we can go for the 3-level system as well. Yes. Okay, sorry. I was explaining that one. Then, of course, we need to find the lifetime of that qubit. And for that, I already told you that instead of taking time that one, by using that 2-qubit system or the range of that 2-level system, we determined that the lifetime of the qubit is of the order of the second, which is very good regarding that plasma or the quantum dot or some of the qubits, which I am giving the answer to the Yusuf question regarding that one. However, we can also consider that the rotating wave approximation, which we use to determine the Hamiltonian, is also satisfied where the gamma should be much, much less than the transition frequency. But the major limitation to our model comes with the quantum diffusion due to the background fluctuations, due to which which can be evaporated within some certain time, and due to which the lifetime of this qubit can be decreased by maximally 20%. We have calculated that theoretically as well. But I am writing that at the end before defining that one. In other words, I have written this qubit lifetime after calculating or determining this quantum diffusion or the drawback of this qubit as well. So, but in any means, this qubit lifetime is very good, not for all with respect to all, but with respect to many other qubits with respect to which we can use to perform the quantum info protocols that I will compare at the last of this presentation, some of the qubits, not all. So now, if we follow the very similar procedure for the 3-level system, I don't need to go to the details of that system. We can determine the transition frequency, spontaneous decay rate, and everything, whatever we want to determine. So due to this large lifetime of the qubit, fortunately, we got the physics synopsis from the APS editor, which he mentioned that this qubit needs the top when compared with the other lifetime of the qubits, and perfected with the lifetime of the qubits that are already perfected in the lab with respect to that matter wave qubits here. So now, if we have that qubit, the first property or the first thing we need to determine the lifetime, which we have seen now. Now comes to the point, okay, if we want to observe the information or if we want to proceed with the information protocols, we need to first observe the fundamental properties. And that fundamental property is the entanglement. And for that entanglement, we place 2 dark-soliton qubits together in a Bose-Einstein condensate having some separation distance t. Another system, of course, I don't need to explain everything again because impurities, BC, and other things I have explained already. But the first question, if we place 2 dark-solitons together, do they not repel each other? Or if they repel each other, can this system be collapsed of the 2-level system? It means that they are going to be dispersed very away and cannot transform information over one to another. But we did that calculation with respect to very short range potential and determined that due to this repulsive interaction, maximally these solitons can be displaced by 0.090, which is much, much smaller than the distance between these 2 qubits. It means that we can ignore this one, short range potential, or we can ignore this repulsive interaction between these 2 qubits. But to confirm that, we also need to confirm that by using some numerical analysis, and we place around 24 solitons together in a BC, having some separation d distance, and we check that the inner solitons remains the same, very similar to like this one. However, the outer solitons feel a much larger repulsive interaction. So the good thing is that we can have in this work or in this slide, the 2 solitons can be placed, or 3, 4, 5, 6 can be placed. But the drawback is that regarding the scalability of that one, we cannot go towards the hundreds qubits in that system. We can have around 15 or 20 with respect to our model. We can place in the 1 BEC at the moment, whatever the researchers have determined with respect to those conditions. We can place around 20 solitons together in a BEC to understand the many-body dynamics as well. So it means that this repulsive interaction can be ignored for our model, and we can proceed with respect to that entanglement dynamics. And for that, we again determine the interaction Hamiltonian. I will not explain that one now because the sigma is the system operator, Bk is the environment, and Gk is the interaction between these two. Very similar approach, but not the same, of course, like the 2-level system we have determined that. Okay, so we derive the master equation with respect to that one, and where the eta ij is the qubit-qubit interaction, shows the non-trivial behavior with respect to the distance between the qubits, but which is very, very small in our case. So it not needs to be explained a lot, much. But gamma ij, where I can be equal to j, I cannot be equal to j. If I equal to j, that comes with the spontaneous decay, which you have already seen with respect to the Wigner-Weisskopf theory. And if I is not equal to j, that comes with the collective damping resulting from the mutual exchange between the mediating particle between these 2 dark-soliton qubits. It also shows the non-trivial behavior with respect to dash distance between the 2 dark-soliton qubits. So what the important point with respect to our system comes with that, we can use this analysis to perform or to use this collective damping, which is the main prominent term in our system, to see how much entanglement or how large the entanglement we can have in our system. Of course, to solve this master equation, we use a collective and decay basis, with the two-level system makes like this system with excited state going to symmetric to ground, or excited state symmetric to antisymmetric or the ground, with the faster or the slower decay with this generic way for the super symmetric or antisymmetric state. And this is just can be analyzed from this density matrix elements as well. Now comes to the point what procedure we should choose to see the entanglement. And for that, we need some superposition of maximally entangled symmetric and antisymmetric state initially, and we use Wooter's criteria for the concurrence or to quantification for the quantification of the entanglement, which we have simplified in this way, where this eta or this term, sign term, depends on eta, which is the qubit-qubit interaction, which shows the oscillation, but our eta is very, very small, which does not show any type of oscillation here. And the gamma, which is the collective damping, gamma 1, 2, where I is not equal to J. On the last slide, I was defining that gamma, which is the collective damping parameter, due to which the entanglement initially follows a fast decay, initially shows a fast decay, follows a slow decay, initially shows a fast increase, follows a slow decay, and having a larger value of the entanglement of the concurrence at larger distances between the two qubits here, which makes our system more worthy. And this all happening is due to the asymmetry between two cascades from excited to symmetric, symmetric to ground, or excited to antisymmetric, antisymmetric to ground. Okay, so this is the concurrence. Very similarly, if we want to see the entanglement decay, how fast, if there is somehow entanglement in the system initially, we have how the fast or slow the entanglement decays. For that, we choose this state, but the concurrence is defined two alternative ways. Because of the eigenvalues of the Wooter's criteria, we can define two alternative ways because of this point here. But here, the condition comes to that this should be greater than this one, and these two states should not be equally populated initially, if we want to define with respect to those eigenvalues or the system by using the Wooter's criteria. We see that the initially, if you will see that here, the initially entanglement shows the exponential behavior. However, later on at around alpha equal to 1/3, entanglement dies and then regenerate due to this C2 parameter here. Initially comes with respect to this one, and then C2 with respect to this one, and regenerate in this value. This is the time period between these two points here is the dark period, which is the entanglement sudden death, entanglement birth to minus entanglement sudden death. That is the dark period, which we have calculated, which is the 16 millisecond for our model. And for other model, if we consider, if we see other systems, this is much, much greater than that one. But however, if you will see that the D is not much greater than the healing length between the two dark-soliton with respect to that solitons here. D is approximately equal to xi, you can say that. But if we consider D is much, much greater than xi, then there is no revival comes, because the rho Eg 2 times rho of G comes with respect to the rho AA, and there is a negative. So just the one state comes with respect to that one, and the entanglement does not revive with respect to that system. However, we can say that if we want to decay or delay this time dark period as well, and for that we need to use some time of unity operation or qubit by following some of the researchers have done work on these research papers, we can more delay this dark period of the entanglement between these two. Now the last point of this section 2 comes with respect to that point. We have seen that we have larger concurrence at larger distances. So it means we verify that results with respect to the steady state concurrence by using some laser scheme, externally driven laser scheme. And we have seen that at D equal to 5/2 micrometer, we have larger distances, large entanglement, steady state concurrence here. Another important point is that the Rabi frequency which we use for this laser scheme is much, much less than the already that people are using around 1 kilohertz with respect to that one, and we can use just a 5.5 hertz Rabi frequency to have this steady state concurrence for our model. Now, the remarkable and the appealing feature of this dark-solid qubit is the achievement of steady state concurrence for distances that are much larger than those obtained in other physical systems, like the plasmons and the quantum dots and some of the others. These people have done that for quantum. Now comes to the another point of the last section of this presentation, section 3, where I want to mention that I will not go into much details because of the system is already defined here. How to see the acoustic analog of electromagnetic induced transparency. Mean to say that electromagnetic induced transparency is a very fundamental or very interesting application with respect to the qubit system here. And for that, we place many solitons in a system or array. We place that soliton in an array and derive externally with the probe and control laser, the lower 2-level system with the probe and upper 2-level with the control laser. And of course, doing the very similar mathematics, which I have defined, that we need to, of course, find these conditions for the 3-level system already mentioned. We need to write the Hamiltonian already mentioned. I have that, those things, the decay rates, everything is mentioned. Just with respect to that separation, we need to find the susceptibility and see that how this behavior comes with respect to that one. How we can see that the trapping of the sound here, like electromagnetic or the trapping of the slow pulse or the slow sound here. We see that initially it follows the initially it shows the Lorentzian peak with respect to that small value of the omega c with respect to that decay rate. However, as we increase this omega c or the coupled laser frequency, immediately the dip appears, but this dip does not go to 0 because of the large value or the small difference between these two decay rates. But this transparency window is very narrow, which tells us that we can have very slow sound. We can have very slow sound here. And if you will see that, we determine that the VG or the group velocity with respect to that slow pulses is 0.06 millisecond, which is very, very slow, which is very, very large, or which is very, very good value with respect to the already experimental perfected in lab is the 9.8 millisecond here, which due to that process, I would say that this paper, this work is interesting with respect to that 3-level system as well, instead of just the 2-level system or the entanglement. Largest is entanglement and the slow acoustic pulses, and we have this remarkable result for the experimentally predicted 9.8 meter per second with respect to the sound pulses here. Of course, this point is just to make sure that the transparency window which we obtained on the last slide here, this one is exactly perfectly matches with respect to the dispersion curve by having this solution of Heisenberg relation. Now, let me compare these results with some of the already protocols which Yusuf was saying at the start. If you will see that the lifetime of this surface plasmon is in femtosecond. Quantum dots with respect to performance system is a picosecond. In our system, we have in the second orbit. The concurrence lifetime is nanosecond. Here, the quantum dots with respect to the picosecond, and dark solitons have the millisecond. And the steady state concurrence is lesser. Fidelity with respect to some gate is lesser, but the distance between our system is in the micrometer instead of the nanometer with respect to that other protocols. And just to summarize that one, these dark solitons, I would say that this is the excellent candidate to store information over the larger time scale, but limited due to the quantum depletion of the soliton or regarding the scalability. However, these are the appealing candidate for the quantum memories or the quantum gates, because no one is working on this project or on this analysis, I think so, in the whole world, not regarding the Bose-Einstein condensate, nor regarding the solitons. Bose-Einstein's condensate with the soliton in quantum information theory. These are the work which I have done with respect to these models so far, but I am expecting to do these analyses more and many other very interesting properties with respect to this dark-soliton qubits in future, whenever I have some time or in accordance to that one. So let me summarize. I have summarized that results, and let me tell you very briefly what the other systems I have done by using the plasmonic surface and by placing two-level systems very similar to the dark-soliton Qudits. And by placing this B0, by applying this V0, we have the non-reciprocal and non-reciprocity in the system. And we observe by different quantifications of quantification of the entanglement. We use this concurrent state discord and activity. We determine that one and the dense coding capacity for this system as well. And then the very interesting aspect of the quantum friction regarding that, we place two-level system or the two-level atom with at distance d from the metallic surface, and this level is moving with relative velocity v. And then we have seen that important aspect of the chiral transition with respect to that quantum friction here in this paper, in this research work. This is not published yet, but submitted to the some aspect. And this another interesting work with respect to that, a graphene model having optical frequency placed between the two parallel plate capacitor parallel plate capacitor have the frequency microwave range. By exchanging the microwave to optical frequency, we have the soliton appearance in this model as well. And thank you so much.
If there are no more questions, let's thank our speaker again.
Thank you.